Hey, how's it going, everybody? Welcome back to my bench. Today we're going to be talking about the new Radiomaster MT12 Surface radio. It's their first surface radio after kind of taking over the air radio market. I started recording a video with some of my opinions, and it just got to be way too long. So in this video, we're just going to focus on just the facts. I'm going to go through here, test every protocol that I have available to me, test it for compatibility, and test it for latency, and we can see how it works with this radio. And let me just say right up front, nothing I am saying that might come across as negative is aimed at the open source developers. EdgeTX, which is forked from OpenTX, Express ELRS, the multi-protocol module inside of here, those are all amazing projects run by people who their passion is developing code to help everybody else in the community, and I think that is awesome. This is a Radiomaster product, and it's on them to make sure that the radio is as good as it can be. So again, no hate towards the open source developers. So first, before we get into latency and protocols, I want to give a little bit of background on servo PWM and latency. I think a lot of people in the surface hobby talk about latency and they talk about servo refresh rate, and they might not know exactly what they're talking about. So hopefully some of this will be educational. All right, so how does PWM work for controlling servos? You can see here, this is the train of pulses that is coming across to tell the servo what to do. In this case, we are at a 100 hertz refresh rate, so a period between pulses is 10 milliseconds. And right now we're in the middle of travel, so it's around 1.5 to 1.6 milliseconds. You can see when I pull the trigger, the servo moves from center to one direction, and you can also see that pulse width is now 2 milliseconds. When I go to brake, you can see the servo moves the other way when I brake, and that pulse gets narrower, gets down to its roughly 1 millisecond width, and this happens to be 1.1, but so that's the range from roughly 1 millisecond to 2 milliseconds is the range of pulse widths that can tell the servo to move from one direction all the way to the other direction. There you go. Now you're a PWM expert. All right, so what I've done for a baseline here is I've got the Traxxas TQ radio. If you've done anything in Surface RC, you've likely came across this radio. Man, there's got to be hundreds of thousands of them out there at this point. I wanted to use this as the baseline just because so many people have seen it and used it, and it was cheap, so I didn't mind cutting it in half and soldering wires to it. So I've got a rubber band holding full brake, and when I touch this button, it goes full throttle. So that will allow us to do some latency testing. Over here on the oscilloscope, I've got it set up so I can do a single capture. And here we can see when the pulse train goes from thick to thin. And this blue line is when the switch actually happens. So we can see the delay from this blue line to this thin packet. This is when you can see when the packet changed. It changed because of this switch input. So now we can measure the distance from here to here, which is the time delay of the change at the radio, which is the blue line, to the change at the servo, which is the yellow line. And if we run it a couple times here, you can see that was a decently long delay. That was a shorter delay. And that was about the same delay. So we can actually measure that and see how long that delay is. And that's what we'll do now. So that's 12 milliseconds. 16.1 milliseconds. 9.7 milliseconds. 12.8 milliseconds. 15 milliseconds, 14.5 milliseconds, 8 milliseconds, 12.8 milliseconds, 20.7 milliseconds, 19.9 milliseconds, 7 milliseconds, 15.8 milliseconds. Another thing I want to check is fail-safe on all these protocols. as the name implies, fail-safe means that if your radio would fail, the link fails, you drive too far, if your battery dies, if anything happens where it's not talking back and forth, you want the steering and the throttle to fail safe. And the best way to fail safe is just to return to neutral position. So let's turn the power off on the radio here and see if we do indeed fail safe. Yeah, instantly we fail safe. See, we got a blinking red light. And one thing I've found from having this rubber band on is that this system actually, when you turn it on, I don't know what you'd call it, it power on safe. So right now we're at full brake, and then when we turn on, you can see we have a link, but it has not gone to the full extreme yet. It actually waits to get a neutral position before it allows you to command. So that's pretty cool. I didn't know it did that. So what this would do is if you would have your transmitter on and it was like stuffed up against a coat or something, and it's either full throttle or full brake, and you turned on your car wouldn't drive away from you. It would wait until you return this back to neutral, and then it would work again. So just like I did with my Traxxas radio, I've modified the Radiomaster MT12 to be able to monitor a switch output on the oscilloscope, so we can do the same thing where we can see how long it takes from the switch to change for the servo to start to change as well. But before we get into the ELRS protocol and the receivers from Radiomaster, I did want to touch on an issue that I haven't seen talked about with this radio. Some people in the aircraft space have been talking about it. But there is a hardware issue with these PWM receivers that cause a big blast of data on, they say channel 2, but I've also witnessed that on channel 1. This is channel 1 here. So when you power up the receiver, this data gets blasted out on that channel. The data line goes back low, and then here is the normal PWM signal that you would expect to come out of it. But like I said, on boot up, that's what you see. And if we switch it to channel 2 here, you can see a similar behavior where on boot up, a bunch of data happens, the line goes low, and then normal PWM happens. And here we can see what it looks like on channel 3 on power up. This is what you would expect for a receiver. Just the pulse train just starts up and starts going. This can be an issue for you if you're running a gyro or if you're running a programmable servo. I'm assuming even some ESCs that do some advanced communication back and forth to the receiver or the programmer. You might see issues with these receivers plugged into channel 1 or 2. In fact, one review that I watched where a guy was using it on a drift car was having issues with not being able to power up with his gyro and his servo plugged in. He swapped channels around and then it did work. I'm fairly confident that this was the issue that he was seeing. So just keep that in mind if you have some weird issues with an ELRS PWM receiver, that this is a problem on those receivers. All right, let's take a look at the ER5CI Express LRS receiver from Radiomaster. I've got the baud rate cranked all the way up. I'm running at 1000 hertz. And I have Wi-Fi'd into the receiver to update the PWM frequency to be 333 hertz, which is something I haven't heard the other reviewers talking about. Maybe they did it without mentioning it, but it looks like they just kind of bound it out of the box. And as you'll see in a second here, the default configuration for the PWM update is 50 hertz. So, like I said, I got a switch here that I can flip, and we can go ahead and measure some of the latency. This one was 4.4 milliseconds. This was 5.8 milliseconds. 5.8 milliseconds again. 6.9 milliseconds. Nice. 4.4 milliseconds. 4.8 milliseconds. 6.0 milliseconds. 5.9 milliseconds. 6.6 milliseconds. 5.6 milliseconds. 3.3 milliseconds. All right, let's check failsafe now. Again, when we turn off the transmitter, we should see this return back to neutral, which it does. So out of the box, failsafe appears to be configured with these receivers, so that's good. All right, so let's go ahead and check out the Radiomaster ER5CI. This is set up as it is out of the box, so this will be at 50 hertz mode. As you can see, we still have the baud rate cranked up to the maximum and the ELRS refresh rate cranked up to the maximum, but the PWM update on the receiver is going to be 50 hertz. All right, so first latency test, we're at 14.9 milliseconds, 21.1, 23.3, 14.6, 21.5, 22.4, 19.4, 22.5, 8.6, 18.7, 16.5. And again, let's just give it the fail-safe check. And we indeed did fail-safe, so that's good. All right, here we have the Radiomaster R85C. This is the receiver that comes with the multi-protocol version of the MT12. Let's power it on, bind it up. You can bind this in FrSky D8, D16, or Futaba SFHSS. In my previous testing, every protocol operates pretty much the same way with the same latency. That was 39.9, 23.3, 24.8, 40.8, 25.9, 39.5, 45.5. All right, let's see if this receiver is a fail-safe receiver. No, it did not. It is holding the last command it was sent. So if you had this in a model and you either went out of range or your transmitter battery died, it is going to keep doing the last thing it was told to do. And if that was full throttle in a drag race or in a speed test or just far away from you and you lost sight of it, it's just gonna keep driving. So yeah. All right, let's bind up our Traxxas 6519. You can see we've got 6519 selected in the protocol screen. Hold down the link button, plug in power. We get the binding blink sequence. We'll click on bind. It looks like it has started the bind process. And we get a quick green flash and now red flashing error. I am not able to get the Traxxas radio and the Traxxas receiver bound to the MT12, which is a little odd because some influencers were talking about how they were controlling their Traxxas vehicles. So maybe I'm just doing it wrong, but unfortunately I can't do any latency testing with the MT12 with the Traxxas receivers because I cannot get them to bind. All right, moving on to probably the second most popular protocol for surface vehicles, Spektrum DSMR. This is a Spektrum Firma 40 amp 2-in-1 receiver that is in my Axial SCX3. And one thing to note here is that when you get the radio from Radiomaster, default is throttle on channel 1, steering on channel 2, which is just backwards from what it has been always on surface. The saying goes 1 to turn, 2 to burn. So if you would bind this up and not realize it, your steering would do the throttle and your throttle would do the steering. Because this is a 2-in-1, the receiver and the ESC are in the same box and you can't just swap the plugs on it. So let's get this bound up to the Radiomaster MT12 and do some latency testing with it. All right, latency here is 18.9, 19.1, 19.2, 22.1, 19.1, 14.5, 21.1, 12.3, 18, 18.7, 19. I also didn't mention it, but we're on a 90 hertz refresh rate with a period of 11 milliseconds. It appears that you can change some of those settings inside of here. this receiver at least doesn't respect what the radio says. You can change that to 22 milliseconds and it still stays on 11 millisecond period. Let's see if it is configured to fail safe. I believe it's in the receiver, so this should have no problem failing safe. And as you can see, it does have telemetry as well, so that is supported. Yep, fail safe, so good to go on this one. All right, so we got the Losi ProMoto MX. This is a bind button here on the receiver. Turn it on, bind. You see the fast flash. We will select bind here. Bind it up. Goes through its little initialization because this is also a 6-axis gyro accelerometer. We get telemetry over here. It works. So that's pretty neat. Turn the bike off. Turn the bike back on. And it appears to have lost bind. Alright, time to move on to some of the Flysky protocols. Here we have the FSGR3C. It is an AFHDS, the original one that was used with radios like this. If you've been around for a while, these are getting pretty old. Man, 15 years probably now for these radios. So let's see if the Radiomaster combined and what kind of latency these receivers have. All right, so this is a 54 hertz protocol with a period of 18.5 milliseconds, it looks like. Let's do some latency testing. 17.5, 17.5, 21.6, 30.7, 10, that's going to work for it. 30.5, 15.9, 14, 20, and let's see if it fails safe. Passive fail safe, so it's not actively driving any signals, but it didn't command neutral. So kind of a half thumbs up on this one. I believe there is a button here that you can change fail safe, but all right, let's keep it going with Flysky. Here we have the GT5, which is probably the most common radio for AFHDS 2A. And here we have a no-name receiver that supports that protocol. Let's get it bound up to the Radiomaster MT12. You can see there I cranked the servo rate up, but I don't believe the more simple receivers respect that. I think they will be locked in at about 50 hertz. But let's test it and see what we get for latency. 23 milliseconds? And yeah, as you can see, it's running at 50 hertz or 20 milliseconds. 18.8. 24.7. 17.3, 31.4, 21.8, 29.4, 15.6, 22.9, 20.5, 31.1, 18.4. And let's see if it fail safes. Nope. No failsafe. At least not by default. All right, here we have another AFHDS 2A receiver. This is the Flysky FSA3. It looks like this receiver is actually running at 60 hertz or 16.6 millisecond. Again, it doesn't seem to respect the setting here on the transmitter. It doesn't actually change the servo rate at all. 18.9, 20.5, 18.4, 23.2, 23.1, 30.5, 21.2, 15.5, 30.7, 29.1, 19.3. And let's see if it fail safes. Yes, it did. So this has failsafe configured out of the box. Good thing. All right, here we have the Flysky FSBS6. Also an AFHDS 2A receiver. Now, this receiver is interesting because, as you can see, the 303 hertz, it does respect this setting in the radio here, but this is a gyro receiver, and the gyro is active, and there's no way to shut it off from the transmitter. If you look at the GT5, it's got this additional menu here where you can turn on SVC, which is the gyro, and you can like change a bunch of settings on the SVC, and this is all driven from the transmitter. So being that this transmitter doesn't have those options, I don't think you can control that. The funny thing here is that this is plugged into the throttle channel, and the gyro is still doing stuff, so that's an interesting use of the gyro. But just for giggles, let's go ahead and test it for latency. 17.1 milliseconds, 15 milliseconds, 14 milliseconds, 18 milliseconds, 11, 15.7, 20.4, 11.5, 14. And let's see if it fail safes.
Receiver still connected.
The telemetry is working too, because it two-way communication. It knows that the receiver is still connected. So let's see if it fail safes. Yep, fail safe. So that's good. And to continue with the theme of Flysky protocols that I don't believe are fully supported, we have the Axial SCX24, which uses a Flysky transmitter that looks like this. We have the original FCX24 transmitter with the dip switches that is also made by Flysky. And then we have the most recent FCX24 from FMS that also has a Flysky radio. I believe all these radios use a similar protocol. I don't know if they're exactly the same, but they have like the LED for the car battery, and they have some sort of two-way communication telemetry stuff going on that I don't believe is supported in the multi-protocol module. And then some other Flysky protocols that aren't currently supported by the multi-protocol module. The AFHDS3 that is used with the Noble NB4, and the Flysky ANT protocol that is fairly popular with Flysky and OEMs, it seems like. These two protocols, to my knowledge, are not supported yet. A microcrawler that does work is the old SCX24s with transmitters that look like this. This is actually the Pelican protocol and its subtype SCX24. And you can see here, it does indeed function. So let's go ahead and do some latency testing with this protocol. All right, so this is a roughly 60 hertz protocol, 16 millisecond period. First latency measurement is 32 milliseconds, 29 milliseconds, 24 milliseconds, 22.7. Oh, that was a bad one. 43 milliseconds, 29.8, 26.8, 36.5, 23.3. And let's see if it fail safes. This is one of those passive fail safes where it doesn't actively command neutral, but it is not holding the last command. So thumb sideways. These little guys, the Team Associated 28th scale, they're not actually Team Associated. They were manufactured by somebody else who used to be able to buy them from other places, but Associated slapped their names on it, and now you can only buy the Associated one stateside. Had 3 or 4 of these things, but we only got one transmitter left with the steering that still works. Tried to replace the potentiometer in there, but it's a small little thing that I can't find anywhere else. So that's actually one of the reasons I was looking forward to having a multi-protocol, because I figured I'd be able to bind up to these guys and be able to use the ones with broken transmitters and at least get a couple of them revived. But I cannot figure out which protocol they use. If you follow the FCC ID here, 725 is the leading the company code, and then 2014998. Then also 2018998 also comes back to a different generation of these radios. Inside the FCC documentation, it says that it uses Flysky AFHDS, and that is not true because I cannot get these to bind that way. I'm guessing it was just reused paperwork. But yeah, if anybody knows the protocol that these things use, I got the back off of this one. Looks like XN297LB, maybe LBS. That looks like that's the RF chip anyway. The main chip there looks like U3 is totally scratched off, so I can't tell you what that one is, but that's the transmitter. Sure, it'd be nice to be able to bind these guys and breathe some new life in them because they're really fun to drive around the house. All right, here we have the WL Toys K989. This binds in the V2X2 protocol, and you actually don't bind it. You just it just binds to the first transmitter it sees. So if with this protocol on, it'll get bound to it. One interesting thing with this protocol is that the throttle is on channel 2 and the steering is on channel 4. So let's do some latency testing with it. All right, so this looks to be a 60 hertz protocol, not too shabby. First measurement is 30.8 milliseconds, 20.3, 19.8, 19.5, 29.6, 24.9, 24.5, 26.8. And let's see if it fail safes. No. All right, here we have another WL Toys. It's the truck one. Receiver looks like this. It uses the XKX420 protocol. For some reason, it's running at 333 megahertz, and it's making a lot of loud noises. And you're just going to trust me, latency is around 40 milliseconds. I'm going to shut this off before it blows up. So here's all of the data compiled from all of the testing. I have the average latency column here kind of color scaled. My printer didn't print it very good, but you can get the gist of it. Green is the best, red is the worst, and we're kind of going up and down. Basically, pretty much what you would expect. The ELRS running at 333 is by far and away the best protocol. But like the Traxxas radio running average latency of 13.7, best case at 7. I mean, that's doing a lot for a radio that some people just throw in the trash. I was actually pretty impressed by that. In my opinion, this is kind of like, just like I call it, it's the baseline. If your protocol is worse than that, there's really no excuse for it to be worse than that. Speaking of that, this Radiomaster, I'm trying to keep this video mainly facts, but it's tough for me to just ignore this. It is bad. It's just bad. I would not suggest buying these or using these. Even though I got it for free with the radio, I do not plan on putting that receiver in anything. And we can see the kind of second most popular service protocol, the DSMR. Respectable numbers here, definitely not bad. If I had, this 2-in-1, I don't plan on getting rid of that. It functions just fine. These Flysky protocols, nothing really new there. I think that this is kind of a known quantity. These again aren't bad. I have raced with these protocols. The reaction time is noticeable. The lack of response. But for bashing and rock crawling, I personally think that these numbers are perfectly fine. This BS6 with the weird gyro behavior, yes, you can crank up the servo refresh rate, but it doesn't really show that much in the latency. It is slightly better, but I mean it's not 3 times better. It also doesn't work with the gyro stuff. So I don't know if in the future that stuff will be fixed. we'll have to wait and see. And then some of the smaller vehicles that I was able to get supported. The Axial Pelican, again, a little 2-in-1 rock crawler, not really made to have the best latency. And the WL toys, again, thankfully they can work, but I don't know why this thing was running at 333 megahertz. It must have been a setting from one of the other protocols just getting used with that protocol, because when you're looking at this protocol, it does not give you the option to change the servo rate. So it was a little surprising, and like I said, that servo was whining, and it was literally high-pitched whining. It was not liking running that, but the protocols do work. It just might need some tweaking. So I think I've got about 35-ish vehicles, and right now, especially with the Traxxas not being supported, I can only bind to about 14 of them. So about a third of my vehicles I'm actually able to use. Otherwise, they are not able to be supported by the multi-protocol module right now. So remember to keep that in mind. So hopefully this video was helpful for you. If you have anything to add or any questions, feel free to drop them in the comments below.